thermodynamics is going to show up all over the place in biochemistry, especially when we're talking about metabolism, but also with things like enzyme kinetics and even with our buffers. So it's important to review that thermodynamics from chemistry in order to prepare for biochemistry, and then later in biochemistry, we'll get back to it a lot more. So most of this will hopefully be a review from chemistry, and then we'll have a couple new concepts that I just wanted to introduce you to. One of them is going to be just a kind of technicality with regards to transformed free energy changes, where we have a little prime symbol after our delta G naught. And the other is a concept of steady state, which we'll come back to a lot later when we talk about metabolism. But in terms of the review, we want to talk about what makes a reaction favorable, kind of like inherently. So in terms of its enthalpy and entropy, how can we look at a reaction and think, okay, well, is this likely to be favorable or not? Review how we can express this mathematically using delta equations for delta G, both at equilibrium and at non-equilibrium, and thinking about kind of inherent favorability versus favorability under the actual conditions, taking into account concentrations. And this will bring us to this concept of steady state, where we kind of keep things away from an equilibrium. This is going to be an very important topic in biochemistry, but we'll be dealing with it mostly when we deal with metabolism. But I thought I would introduce it quickly here, and your book does and stuff. By the end of the video and your reading and everything, I'm hoping that you'll be able to distinguish between delta G naught, and delta G naught prime. Be able to just look at a reaction and kind of predict whether it'll be inherently favorable, that is held with negative delta G naught. Also be able to predict whether a reaction will be favorable under the given conditions, and do some basic free energy calculations. But my goal really isn't just for you to be able to plug numbers into an equation. I really just want you to know the concepts mostly. That's what I care most about. I want you to be able to look at a reaction and think, okay, well, was this favorable or not, and why, and know what to look for in terms of the signs of the reaction, and whether or not a value is greater than 1 or less than 1 or 0. Basically, just be able to. Let's start by reviewing what makes a reaction favorable. And when we're talking about reaction favorability, we're typically thinking about its in terms of free energy, or this change in delta G. Basically, what you'll see often are things, reaction energy diagrams, where basically you have the energy of your reactants, the energy of your reactants, and you have the energy of your products. And if in between them, you have the change between them is going to be your delta G. So this would be your reactants and your products. And then delta G equals the G of the products minus the G of the reactants. And this is a state function. So what it means is that anything could be happening in between these reactants and the products. And often what you see is that there is going to be a barrier to reaching this. So you'll have some sort of activation barrier. And then we'll talk about a delta G with double dagger. You kind of have this like activation energy. And this can actually make it so that even if a reaction is really thermodynamically favorable, even if the products have a much lower energy than the reactants, it still might not be very likely to happen. And so this actually makes it so that the breaking of ATP, although it's really, really favorable and it's thermodynamically spontaneous, it doesn't just happen in our cells all the time because it has a really high activation barrier. So all our ATP isn't just disappearing poof, which is great. So we'll see also in the lab, we'll see how, or not in the lab, in the class, we'll see how enzymes can lower this activation energy. So they can lower that activation energy and make it more likely. Another thing that we could do is, because delta G is a state function, what we can do is, instead of just having a simple route from the reactants to the products, we can actually have coupled reactions. So we might say have a reaction that's kind of unfavorable, but it's tied to a reaction that's super duper favorable. And so you end up with kind of like a complicated reaction diagram. But by coupling reactions, we're able to then make reactions happen, even if they're not that favorable. So just like you could push a ball up a hill, you can make a reaction go that's not very favorable by kind of coupling it to a more favorable reaction. Or as we'll see, by changing the concentrations of your reactants and your products. In chemistry, you probably talked about a term, Le Chatelier's principle, where basically you have your reactants. If you have some sort of reversible reaction, you have reactants and you have products. Well, what would happen is if you add reactants, you're going to increase the making of the product. So you're going to shift to the right so that you make more products in order to compensate. And if you add more of your products, well, now the reaction is going to be driven to the left. And so then you make more reactants in order to compensate. So you probably talked about that in like your general chemistry class, and we'll see how we can actually put equilibrium constants onto that to really put some numbers onto it and see how we can mathematically express how far away we are from that happy place, from that equilibrium that this is all changing in order to reach, using that delta G. Not the delta G, not that standard one, but looking at how far we actually are from those standard conditions. And that's going to be an important way too in biochemistry, in which we're able to control how favorable a reaction is. But at its heart, the inherent favorability of a reaction is going to come down to changes in enthalpy and entropy. So this delta H is going to be our enthalpy. So this is going to be like our bond strength, our heat, and then our entropy, which is going to be our randomness or disorder. Molecules like being really random and disordered. So if you have more molecules, that's going to be happy. And when we talk about happy, then again, we're talking about a negative delta G. Or if you have more ways the molecules can move or can orient themselves. So we'll see a lot throughout the class, the idea of water wanting to form bonds with other water molecules and not wanting to form bonds with like hydrophobic things. So if you have a couple of hydrophobic things, the water is kind of going to be tied up around each of these, forming this like shell of water around it. And that's going to be energetically unfavorable having that because there's not that much entropy. Those water molecules can't move around that much. But if you had those hydrophobic things joined together, well, now what's actually going to be happening is you still have to have a water shell around it, but fewer water molecules are required because you have a lower surface area that needs to be covered. And so now you've freed up a bunch of water molecules to go hang around. And so you get this entropic benefit. And this can be a way in which we can get like binding energy. So we'll get much more into that later in the course. But for now, just know that entropy is going to be a really big driving factor for a lot of biochemical reactions, as well as if we're talking about like changes. So for enthalpy, this would be things like your bond strength. And we'll also be also interactions. So it's not just going to be covalent bonds. So it's not just going to be more stable bonds. So we'll talk about like H bonds, etc. So it doesn't have to be those covalent interactions. And we're always going to be talking about the difference between like the bonds that we started with and the bonds that we ended with. And if we have more stable ones to end with, then we'll get a negative enthalpy. So there are different ways that you can get to having a negative delta G. So we need to look at this equation. And if we want in order for it to be more likely to have a negative delta G, we want there to be a lower enthalpy. So we want the low H is good in terms of favorability. But what about our entropy? Well, here we're actually subtracting the entropy. So we want an increase in S. An increase in S is happy. But it's the combination of the H and the S. Both are going to come into play in order to decide whether a reaction is actually favorable. The effects of the entropy are multiplied by the temperature. So if you have something that is has a big entropic benefit, then it's going to be more favored at a lower temperature. At a higher temperature. But if you have something with an entropic cost, so that has like a positive entropy, well, then increasing the temperature is actually going to make things worse. So you want to be thinking about the different ways, the different combinations of ways that a reaction could get to favorability. So you're always going to be best off if you have an exothermic reaction. So you have a delta H that's negative and you have a delta S that's positive. So you're increasing the entropy. That's always going to be negative, always going to be spontaneous. Conversely, if things were the opposite, if your reaction was endothermic, so you had a positive delta H and a negative delta S, that would always be positive, always be non-spontaneous. And in either of the other cases, if one of them is good and one of them is bad, so you have a negative delta S or you have a negative or you have a positive delta H, in either of those cases, the temperature is going to make things, is going to decide what's going to matter more. And so one of the things that we'll look at is if you see a change with the temperature, if you see a change in your delta G, then this could be indicating that entropy is having an effect. A lot of times you have a sort of complex mixture of forces that are determining whether something is going to be thermodynamically favorable or not. We often talk about ATP as being what we call like high energy because it has a delta G of like splitting ATP into ADP and your orthophosphate, so just like a free phosphate group. It has a delta G of around minus 30 kilojoules per mole, or about like 7 kcals per mole. Basically, it has a very favorable delta G. And it has that high activation energy, so it's not just going to split off all the time randomly. But so we often talk about these ATP, these phosphoanhydride bonds between those phosphate molecules as being like high energy. I like to think of it as kind of like having a clamped spring, and those holding those phosphate groups together is going to be kind of like holding a tight spring together. And if you were to release one, well, then something can, it goes like flying. And so similarly, the ATP, those bonds are kind of like high energy. And so you think, okay, well, if you release it, then you get that energy that was held in those bonds and you can use it to do other things. And so thinking about things intuitively like this works, but things aren't quite that simple. And so there's going to be complications in terms of all sorts of things. But one of them is that anytime you break a bond, it's always going to have to put in energy to break that bond because of that enthalpy. It's always going to be endergonic and require energy in order to break a bond. What you have to think about instead, though, is remember that we're talking about like the difference between the reactants and the products, and we're talking about like all the products and all the reactants. So you have to take into account things like all of those water molecules that you can now have increased, you can now have those like H bonds and things like this. You get solvation, you get an increase in your enthalpy that way, and you get increased resonance and things like this, as well as often that that you are going not just to ADP, but you're actually, if you go to like AMP, and then you break off those two phosphate groups that are left over, you can get an even more of a boost. So you always need to be thinking about what you're trading for, thinking about the free energy of your reactants and the free energy of your products, and taking into account all those interactions and not just the not just the bonds that it looks like you're looking at right in the equation. But speaking of equations, let's just go in and talk about how we can think about delta G in terms of an equilibrium constant. Basically, we can write this equilibrium constant where if we had a reaction, A plus B is reversible reaction, and then it goes to C plus D. Your Keq would be the concentrations of those parts of the products over the reactants, and then they're to the stoichiometric coefficients. But often we simplify this by writing concentration of our products over the concentration of our reactants. And if we had a single reactant, a single product, and they were reacting 1-to-1, so we didn't need to worry about stoichiometric coefficients, then this would hold true. But if we have multiple reactants or we have multiple products, then, and if they have stoichiometric coefficients and stuff, then we have to use this more complicated thinking about it, like multiplying them together raised to their coefficients. So just remember, like, multiply them and don't add them. And then if you have the stoichiometric coefficients, then you're going to need to raise to them. Remember that when you're at an equilibrium, it's a dynamic equilibrium. So you're still going forward and you're still going back, but for each one that goes forward, you have one that goes back. And that's the dynamic equilibrium that we're talking about. And we'll see later how this is different than the steady state. So, but we have this dynamic equilibrium, and different, depending on how favorable the reaction is, when you reach that happy place, there might be more products or there might be more reactants. If the reaction was really, really favorable, you're going to have more products than reactants. And so what this means is that then you would, if you have more products than reactants, you'd have a number that was greater than 1. So if your equilibrium constant is greater than 1, then the products are thermodynamically favored. But if your reactants, if you have more reactants at equilibrium, so you have more of those reactants left over, well, then you're going to have you'd have the bottom be bigger, so you'd have a number that's less than 1. So if Keq is greater than 1, that's going to be thermodynamically favorable, and if it's less than 1, it's going to be unfavorable. And remember that we'll see how this is related directly to the idea of thermodynamic favorability that we can express with our delta G. We can connect delta G and Keq using this equation. Now here we're showing standard free energy change. So we have this delta G naught. So basically, this means it was measured under standard conditions, where basically that means there's 1 molar concentrations of everything and the temperature is 25 degrees Celsius. And people have measured all these different reactions under these standard conditions, and then they put the values in a table that then you can go look up. But then maybe you have, this is only true for like that certain temperature that it was measured at. And so what you can do is if you have something that's at a different temperature, you can take the temperature into account through this equation. And then the R, this is just this gas constant. So that's how you get this equation. And basically what it's saying is that you can relate the standard free energy to the concentration of your products over reactants at equilibrium. So remember, we're talking at equilibrium. This is the Keq. Keq is at equilibrium. You can get that ratio by taking into account that the gas constant times the temperature in Kelvin times the natural log of your Keq. And if you rearrange things a little bit, then what you can get is you can get Keq is equal to E to the minus delta G naught over RT. So basically, you just rearrange that, and now you have a way to figure out Keq. And why that's important is because now you can figure out how much of the products are there versus the reactants at equilibrium, though. Remember, this is saying that you let it go all the way to equilibrium. And if it has a high activation barrier, it might take a really, really long time to get there if you don't have any help. But thinking in terms of these delta G naughts is able to kind of like tell us about the inherent favorability of the reaction. So let's look a little more explicitly at the connection between Keq to delta G, in this case, delta G naught. So basically you can go directly between the two of them. And let's remember back to what our KEQ was. Remember, that's our products over reactants. Taking into account that this, remember, is a simplified notation for writing it, you need to take into account that you need to multiply together the different components and raise them to the stoichiometric coefficients if applicable. But thinking about just that products over reactants, we can think that, okay, well, if a reaction is favorable, so if favorable, what would we expect? We would expect to have more products than reactants. So we'd have products over a little bit of reactants. Because remember, this is what's happening at equilibrium. So no matter if you started with a bunch of reactants, well, then they go and they react, and so you get more products, and you end up with an equilibrium where you have more products than reactants. So then the KEQ is going to be greater than 1. But if not favorable, what you'd end up with is no matter what you started mixing, you get a little bit of products and a lot of reactants. And then your KEQ, therefore, would be less than 1. And when we're talking about favorability, if something is favorable, then our delta G is going to be negative. And if something is not favorable, we're saying that our delta G is going to be positive. And in this case, we're talking about our delta G naughts, but that same thing holds true even under non-standard conditions. So we have this relationship. And now let's look at our what would happen if we had equal amounts. Well, if we had equal amounts, if products equal reactants at equilibrium, then we would have KEQ is equal to 1. And what we would have was that our delta G was going to be 0. Because remember, we have this equation where basically if we're saying that we have the natural log of 1 is going to be 0. So this is going to be 0. And so your delta G naught is going to be 0 if you have equal amounts of products and reactants. And that makes sense because there's no, basically this is not more favorable with the reactants or the products. So you have that balance. So that would be our middle state. And then anything this way is going to be favorable. And anything this way is going to be unfavorable. And when you're thinking about your KEQ, remember you're thinking about your products over your reactants. And so if you have something, you have a positive, you have a big number for your KEQ, you're going to have a small number for your delta G. You're going to have a lot more products than reactants. If you have something where you have a small number, so this for KEQ, it's always going to be positive, but it might be like 0.00000 something, then that's going to be unfavorable. What that's saying is that your reactants, you have way more reactants than your products, so that's going to be a small number, and your delta G is going to be a big number. So remember that a delta G naught of 0 is saying there's equal amounts of products and reactants, and anytime you're away from that 0, you're going to have more of one than the other. If you go in the negative direction, you have more of your products. And if you have in the positive direction, you have more of your reactants. And we can think about how much more by thinking in terms of that KEQ. So if we had a delta G naught of minus 1.36 kilocalories per mole, then we would have 10-fold more of one of them. And so since it's negative, we'd have 10-fold more of our product. And if we had 100-fold more of our product, then we would have a delta G naught of minus 2.73. So if you have anywhere between like 0 to 2 kilocalories per mole as the delta G naught, so in either direction from that, away from that 0, that's telling you that you have more of one than the other. Yes, anytime that you're away from that 0, but you'll have still pretty significant amounts of both of them. But once you start getting above really 2 kilocalories per mole, somewhere between like 2 kilocalories per mole and 5, you have mostly one of them. So for like 2.73, that would be 100 times full, 100-fold more of one of them. So once you get above like 10-fold more or whatever, once you get above that 2 calories per mole or so, well, then you're starting to say you really predominantly have one of them. And if something is greater than 5, you can pretty much think of it as being all of one of them. But remember that this is at equilibrium, and not reactions often don't reach that equilibrium in biochemistry. Speaking of that equilibrium and that standard free energy change, this is under the standard conditions that are used in chemistry are pretty unideal for those used in biochemistry. If you think about what it means, you're saying you have a 1 molar concentration of everything. Well, even just thinking about from the very beginning, the solvent that our cells are like bathed in, that are contained, that all the molecules, all this stuff is happening in, is water. And water has a concentration of 55.5 molar. So water is going to be way higher than that 1 molar concentration. And so if we're thinking about only having a mole of water's worth, and then our water's in the reaction or something, well, then we're going to get a very unreasonable number. And so we want to take this into account as well as other things. And that was like pure water, but what about those protons? Well, if we think about the standard conditions, it would be telling us that basically that would mean that we have 1 mole of our H3O plus. And if we think about pH, well, pH is going to be the log of 1 over the proton concentration. And if we're going to saying that this is 1, well, now we get pH equals log of 1, which is going to give us 0. And so this would be telling us that under these conditions, we have a pH of 0, which is not very relevant at all. So instead, for biochemistry, what we have is we use these like transform standard free energy change, and we represent this with this little prime symbol. So you'll see like delta G prime not, or not prime. You'll see it written both ways. And this is telling you that basically when it's applicable, this was measured, assuming the pH was 7, the water concentration is taken to be 55.5 molar, and your magnesium concentration, if it's applicable, is going to be like 1 millimolar. So you often see this prime notation telling you that this is where this measurement is. And so you'll see this a lot throughout the book. Sometimes they kind of go back and forth between the two of them, and I'm not always sure which ones they're talking about. But for most things, it's not actually going to make a difference because those things didn't come into the play with the equation. So that was at equilibrium, but we can also do something when we're not at equilibrium, which is pretty much all the time in biochemistry. What we need to do is now what we're going to do is we're going to say our delta G, and here this is not with the not sign. This is our actual free energy change. So the one that we're actually going to be like measuring. It's equal to the standard free energy change. So this could be your not, or this could be your not prime in either case. But it's going to be now that standard free energy change that you say get from a table, you're going to adjust it for the conditions that you have. You don't just need to adjust the gap for the temperature, but you also need to adjust for not having that KEQ. Instead, you have the Q. So our KEQ was that concentration of products over reactants at equilibrium. But when we're not at equilibrium, we can do the same sort of thing. We can write the same sort of equation with our products over reactants, but it's not going to be at equilibrium. It's just at whatever point we're measuring. And we call this Q the mass action ratio. And we can do this for any sort of reaction anywhere along its path to equilibrium. And again, we have to take the same things into account, raising to the stoichiometric coefficients, multiplying the different things. But again, we still often abbreviate this as products over reactants. But just remember what we're talking about. You're going to need to be multiplying if applicable. So now we can take this equation and we can have a way to go between that delta G naught that we can get from a table and if we know the concentration of the various things, we can go ahead and we can calculate that change in free energy. So the same equation is actually holds true, and is where the other thing came from, when we're talking in terms of a reaction at equilibrium. Because at equilibrium, this equation kind of just simplifies. So remember that if we're talking about the mass action ratio, if we're talking about Q in terms of an equilibrium reaction, then we can call that same thing Keq, our equilibrium constant. So we can just plug that part in. That's how that changes. And then because at equilibrium, your delta G is going to be 0, what's going to happen is that you can plug in 0 for this delta G, rearrange, and this is how you get that delta G naught equals minus RT line Q, Keq. And then you can also rearrange it in this format. So all of that is coming from this same general reaction, general equation where you have your delta G, so your actual change in free energy is equal to delta G naught, that thing you can get from a table, plus your RT natural log of products over reactants. And again, this delta G is still that same delta G we're talking about that we can think about in terms of our entropy and our enthalpy. If our Q is greater than our Keq, we have more of our products. And if our Q is less than our Keq, we have more reactants. And we're not talking then like wanted. I'll say wanted, but this is just talking about like at equilibrium. Then wanted. So remember, no matter what you start with, no matter what equation, you're going to end up with some sort of Keq where you have products over reactants at equilibrium. And if the reaction is really, really favorable, you could have a ton of P and a little bit of R. And if it's not very favorable, you could have a little bit of P and a lot of R. Now, if we take one of these, no matter which one we take, or whatever, we take any reaction and we perturb it from equilibrium, it's going to go and want to reach that equilibrium again. And so it's going to do whatever it needs to take, whatever it needs to do in order to reach that equilibrium. And so if it has more reactants than it wants, it's going to be pushed towards the products. And if it has more products than it wants, it's going to be driven towards the reactants. Even if you just think about things randomly, like if you have more product molecules around, it's more likely that even if they just randomly happen to convert, you have more of those random chances of occurring. So you can think of everything all as being like super probabilistic as well. But let's take the situation where we have this really favorable reaction and we go and we perturb it. And so maybe we add a bunch of reactants. So we have our P, we have a big P and a little R, and that's at equilibrium and it's happy. But now we go and we stick a bunch of reactants in. Well, now what's going to happen is some of those reactants are going to start reacting and they're going to go to products. So remember, we have our reactants going to products. And if we add reactants, we're going to be driven towards the formation of products. And if we add products, we're going to be driven towards the formation of reactants until you get that balance back. So initially what's going to happen is you're going to start making more of your products. So you're going to get more of your P and less of your R. And then you're going to end up with more of your P and less of your R. And you're going to end up with more of your P and less of your R. And then you're going to get back to the same ratio of P to R. And so note that now we're going to have more of each of the P and R, but the ratio between the two of them is still going to be the same. But as we'll be getting closer and closer to that, as our Q gets closer and closer to Q, well, now what's going to happen is that the drive for that reaction to go in that direction is going to be decreased. If we rearrange that equation that we were looking at before, we can get it to delta G equals minus RT times the natural log of Keq over Q. And I love looking at it this way because this is a reminder that it's really that ratio between the Keq and the Q that's going to directly influence the delta G. So the saying, well, if your Q is equal to Keq, you're at equilibrium. And if you're at equilibrium, then your delta G is 0. There's no drive to do anything. So if we had things at equilibrium, nothing would happen in our cells. But What if our KEQ is different from our Q? Well, if our KEQ is greater than our Q, then this delta G, we're going to be more favorable. And we said that if our KEQ is greater than our Q, what that means is that we have more of those reactants than we kind of want, so we're going to be driven to make more products. This is going to make this number bigger. It's going to give us a bigger negative delta G, more favorable. And if you have more of your products, then you have a bigger Q than KEQ. This value here is going to be a fraction. It's going to be less than 1, and then therefore this the natural log of it is going to be negative. A negative times a negative is going to give you a positive, and therefore you would have a positive delta G, telling you that it's not favorable. So, but that's the sign. So is something favorable or not? But what about the magnitude? Well, we have this relationship where it's this ratio that matters. And so as you get closer and closer to that equilibrium, that ratio between the two of them is going to be decreasing. And as you're nearing that equilibrium, the effect of it is going to be smaller. You're minimizing the effect in either direction. You're going to have less of an effect. The delta G is going to be different. So when we're talking about the actual delta G, what we're talking about is how far are we from equilibrium? And so if we're really far from equilibrium, then we're going to have a very favorable reaction, even if inherently it's not that favorable. And so basically in this way, if we are able to control the concentrations of things, if we're able to control the concentrations of those products and of those reactants, well, now we have a really powerful way to drive reactions. And one of the key places that we'll actually see this is with ATP. So if you don't do anything, eventually you're going to get to delta G is 0. You're going to get that equilibrium. But you can actually do things to prevent this from happening. And so we'll see later in the course. So I just want to introduce the concept to you now, but we'll see a lot more of it later in the course, especially in the context of metabolism, how by keeping things away from equilibrium, by removing products, channeling them into other pathways, shipping them out of the cell, or by adding reactants. So making more of our product, making more of our reactants, say, such as ATP. We'll see this with ATP a lot. We keep a really high concentration of ATP. By doing all of this, we're able to keep things away from reaching that delta G. And there's this idea, this concept of the steady state, where basically you have an equal ratio of your products to reactants, not because you're at equilibrium, not because the forward and reverse rates are the same, but because you're replenishing. And so we're going to see this come up a lot more when we talk about metabolism. I just wanted to introduce you to this concept now. Your book introduces you to this concept now. So it's just something to be thinking about, that we have ways where we're going to be keeping things from reaching that equilibrium. So in terms of what you'll be expected to do, I want you to know the difference between delta G naught, and delta G naught prime. So remember that with delta G, we're talking about the free energy change between products and reactants at any time, whether or not we're at equilibrium. When we're talking about delta G naught, we're talking about the standard free energy change. That's when we measure the free energy change when it reaches equilibrium under those standard conditions. And then the standard conditions are slightly modified in biochemist sense. So we think about things in terms of having a realistic concentration of water and a realistic pH. I want you to be able to predict whether the reaction will be kind of inherently favorable. So it had that negative delta G naught without using math, by just thinking about, do we have more stable bonds formed? That is, do we have a negative delta H? And do we have more entropy? Do we have a positive delta S? And how would that be impacted? How would temperature impact the delta S? It increases that factor. You can also, I want you to be able to predict whether a reaction will be favorable under the given conditions. So by using those math equations, taking into account your KEQ, taking into account your Q and your versus your KEQ, and both just intuitively as well as actually putting numbers to things. So hopefully the beginning of this, a lot of this was just review, and these new concepts are going to be reinforced over and over and over throughout the course. And really, I care less about the actual math then you being able to know the concepts behind them and to kind of think about, okay, well, if how do I know something's favorable or unfavorable given the conditions? By thinking like, am I less than 1 in my KEQ? Am I great? By thinking like, am I less than am I less than 0 in my delta G? That would be favorable. Conversely, if I was greater than 1 with my KEQ, that would be favorable. And so know those trends, know what you should be looking for in order to tell whether something's favorable or unfavorable. And then remember that relationship between your KEQ and your Q.